Playtesting is a common practice in the game research and industry to identify design flaws and evaluate player experience before deployment. There are many types of playtesting used to assess game quality, such as usability testing, balance testing, and accessibility testing. While playtesting is widely practiced, analyzing the data it generates remains a challenge, especially for motion-based VR games. These games rely on multimodal inputs like body movements, gaze, and interactions, making the data inherently multidimensional and difficult to interpret. Previous research has either worked on visual analytics for sports games or just focused on analyzing biometric and physiological data related to player experience. In this work, we aim to streamline the game analysis workflow through exploring the design space of visual analytics. To better understand playtesting workflow and its challenges, we conducted an interview study with 30 practitioners in the VR domain and come up with 3 challenges and design criteria. Based on design criteria, we propose HieraVisVR, a visual analytic tool for reviewing playtest results of VR games or motion-based games in a top-down hierarchical manner. It includes 3 stages: exploration stage, which gives designers an overview of how players interact with the game; grouping stage, which helps uncover interesting gameplay patterns; explanation stage allows designers to investigate individual gameplay experiences in detail and compare players side by side. Let's follow this hypothetical game designer who has developed this motion-based game called Reflex and collected playtesting data with 27 users. Her goal is to understand how novice players experience this game level. She first starts with the exploration stage, using the replayer to get an overview of how players interact with the game. The replayer offers 2 anchor modes: level anchor and event anchor. With level anchors, she directly jumps to a specific chunk of interest. Right away, she notices some players are significantly delayed due to repeatedly bumping into an obstacle barrel. To identify all players who bumped into the obstacle, she moves the grouping poses stage where she specifies clustering criteria for grouping. She selects obstacle hits as a feature and uses k-means as the clustering algorithm, setting the number of groups to 2. Next, she moves the grouping results sub-tab to review the outcome. Now she can select a group and replay the data, focusing on the group of players who are struggling. To further understand why this obstacle is challenging for one group of players, she transitions to the explanation stage. Here, she compares player 6, who frequently collided with the obstacle, to player 3 from their group. Replaying their performances in a VR point-of-view mode, she quickly observes that player 6 spends a significant amount of time looking at the controller, attempting to use it to navigate around the obstacle. She then can draw her observation. We recruited 5 game testing experts who have at least 2 years of game testing experience to evaluate our toolkit. In this study, we asked participants to follow a VR testing questionnaire when they evaluate a VR motion-based game. They were also encouraged to explore freely. Their feedback from the interview confirms that HieraVisVR is intuitive, useful, and helpful when doing playtesting analytics. We applied our toolkit to 2 different applications to demonstrate the flexibility of our framework. This first example is a VR training scenario based on a previous fire evacuation drill. Researchers examined how collaborative behaviors changed as the difficulty of evacuation scenarios increased. In each training scenario, 5 virtual students await rescue. Several in-game metrics were collected for evaluation, including completion time, volunteer trajectories, extinguisher usage, and command times. Here we show the explanation stage of the application, offering a side-by-side comparison of 2 pairs of volunteers participating in a fire drill practice scenario at the same difficulty level. Custom annotations are implemented in this application. For example, fire extinguishers appear when volunteers first encounter a fire, and commands are shown as volunteers instruct virtual students to follow. The second example is the escape room game. Players are required to solve 3 poem-based puzzles, identify the locations of 3 hidden items, and search the room to find them in order to escape. We demonstrate how game designers can use the eye gaze grouping stage of HieraVisVR to identify gaze patterns across tasks or distinguish search behaviors among players completing the same task. This is the end of our video. Thank you for watching.